Hello students, today we are going to see modeling of power system network from generation to distribution. So to create a simple power system network from generation to distribution, we are going to use a SCILAB software and we are going to compute the line current, load voltage, power delivered and system losses. So we are going to take a simple single line power system consisting of, now we are considering the problem statement with the consisting of 11 kilovolts and connected to a transmission line and distribution line. So we are having different impedances here, just I have tabulated here. Generator internal impedance, that is a 0.5 J1, transmission line impedance ZT is equal to 2 plus J4, distribution line impedance ZD is equal to 1 plus J2, load impedance is Z load 10 plus J5. See, you can take any of these values. It is not compulsory that you should take these values only. Just I have taken one sample calculation and 11 kilovolts. So here the main motto is to calculate the values of the total impedance of the system, the line current, the voltage across the load, the complex power delivered to the load, the total system losses. So you can take any these values and this value also your choice. Take any value, just obtain the values of all this from the calculations. Next, algorithm. For algorithm, we are the same thing. Open synode, the same file. We are saving the file. Then we are going to give some input method. That is, we are giving some directly here the input values. Next, apply appropriate equation to solve this problem statement. Next, use the print, that is our display values for the displaying all the final results here. So theory, what is the theory here is connected. So from generation, it is modeled as ideal voltage source connected with some internal impedance. Next, transmission line is modeled as a series impedance which is connected RT plus JXT, that is for transmission line impedance. Next, distribution is also connected as a impedance, that is RT plus JXD. Next, here the load is represented by the Z load values. Just a equivalent circuit, how it will be, it is starting from generator, then internal impedance, all are connected in series. Next the transmission line impedance, next the distribution impedance, next the load impedance. After that the total impedance will be calculated because they are all connected in series, just a summation of all these things. Next the line current is EG divided by Z total, that is just I am explaining the formulas here how to calculate the values. Next the load voltage is, that is a line that is a line current, that is whatever you are getting from here, multiply with the load impedance, you are going to get the load voltage, and the complex power at the load is, that is S load is equal to V load into I, that is a line current. Next, the losses in a network. So losses in a network is line current losses, that is a line I square, or actually I square impedance here, the total impedance, the losses in the total entire network. So just you substitute the calculation. That first is we are going to get the total impedance value, that you are going to get as 13.5 plus J 12 ohms. Next the line current is, if you calculate the line current, how you are going to get, that is this EG value we have taken it as 11,000, that is 11,000 divided by Z total whole square, that is a magnitude value we are taking that here, 13.5 divided by 13.5 whole square plus 12 square. So here it is in the denominator now, so we are rationalizing that. So just you take the complex rationalizing of this Z total value, because it is a rectangular number. When you rationalize, we will get a complex number, that is a inverse complex number, 13.5 minus J12 divided by mod Z. That is what we are going to do here. We are going to rationalize here to calculate the line current. After computing the line current, that is for denominator computation, we are calculating this 362.25. you are going to get numerator is this one value. So once you calculate the line current value, numerator and denominator, you are going to get the value as line current is this one. After that, we are going to get this rectangular form into polar form also. When you convert it into polar form, you will have a magnitude, that is this value, and the angle you are going to get it as this value. Next, after that, the load voltage, we are going to calculate the load voltage. V load is equal to line current into Z load. So V load value is here is how much, 10 plus J4, that is a what we are going to calculate, that is a line current into load impedance, that is a line current whatever you got here, this we are multiplying with the load impedance. Load impedance we have taken it as 10 plus j5. Whenever you multiply, I have written clearly here, whenever you multiply two things in a rectangular form, what also you are going to get, I have written here. You can substitute. If you know idea how to multiply, it is easy, or you can refer for this. So how we are going to get the real part and the imaginary part. After getting the real part and imaginary part, we got the load voltage also. So load voltage we are getting in the rectangular form, now we will get in the polar form also. In the polar form we are going to get 6808. See, for this conversion you can use your calculator or refer any videos for how to convert this rectangular form to polar form by using the calculator. So after getting that, now we are going to calculate the complex power at the load. So complex power is always we are going to take VI conjugate. So conjugate is VI conjugate. Conjugate means just a reverse of that. So V load is equal to, V load value is this one. Conjugate of this line current is just you take the minus. Actually we got line current as a minus, now we are taking the plus here, that is a conjugate. So in place of minus previously we can substitute here plus, then you multiply these two. Previously we have explained the multiplication of this number, then you are going to get the load, that is a complex load power for the load that you are going to get here. Next is active power. So active power is always a real part, we are already know, and reactive power is imaginary part of the complex number. Just I have multiplied in the megawatts, that I want to convert in the megawatts, that is the 10 power 6, here also 10 power 6 MVAR. Then you can check the equality, that is this can be, you can check also by using this formula also, I square R into, that is I square into Z load, then you will get this only approximately this value. So these are the values are matching here. Just you can use this formula or you can use this formula also, calculating the real power, because to checking purpose only we are checking this, whether we got the same values or not. Now let us go for the SCILAB code. Here the SCILAB code is explaining CLC clear. Just I have taken the generated value is 11E3, that is a 11 kilovolts. For kilovolts we are representing with E3. Next, generator impedance is 0.5, that is a internal impedance of that generator is 0.5i. So where we are representing with the imaginary number, that is a real part and imaginary part. Here also real part and imaginary part, real part and imaginary part. This is for transmission line, this is for distribution line impedance, and this is the load impedance. So percentage I into something value will give us a rectangular form of the impedance. So that there all the three ZG, ZT, ZD, Z load all are connected in impedance form. The total impedance how you are going to get, by adding all these things, then you are going to get the total impedance. Then the line current value is equal to EG divided by Z total. So total impedance you are going to get is this one, and the EG value we have taken it as 11,000. Whenever you divided the line current you are going to get, it is going to display. Next, the load voltage is, multiply this line current with the load impedance, you are going to get the load voltage. Next, the load complex power, how you are going to get, V load, and I told it as you just take it as a conjugate of line current, that is a line current you are going to get here it as a negative value, then you are going to get a positive conjugate of that, you will take it as positive. Next, losses we are going to calculate here. I have used another formula here in the program. Absolute value of I square R directly whenever you multiply here also you will get. But for verification purpose I have used this formula also. Absolute value of line current square into the total impedance. You should exclude this load because we are going to calculate the losses in generator internal impedance, transmission line impedance, and the distribution. So one thing you should remember, you should avoid this Z load, because the losses we are going to calculate only in the generator, transmission as well as the distribution. We no need to calculate the losses in the load side. So displaying of line current, that is a how much we are going to get, displaying of load current, how much we are going to get here, displaying of S load, VA, displaying of editor, we are going to get like this. So output, just you are going to get the output will be like this. So let us go for the SCILAB software. Let us go for the SCILAB. Whenever you go for this, we will go for editor. We will go for editor. So once you go for editor, it will go for the here. Then you execute the program. Here I already saved and executed the program here. Then you execute the program. So whenever you execute the program, directly it will display the values will be like this. How much line current you got here? Line current you are going to get it as value is 455.17, and the load voltage you are going to get is 636574.71.26 values. Next, the power at the load, that is a load power is we are going to get is this one value, that is a complex power. Next, the system losses also we are going to get this. So all the values are will be displayed directly. So that's all in this video. I think so this video was useful for you. So for the exam preparation, if you have any doubts, clarifications, you can contact me. Thank you very much.